Hello, everyone. My name is Shujiang, and today we are talking about the rendered private, making GLSL execution uniform to prevent WebGL-based browser fingerprinting. Browser fingerprinting is a powerful method that websites can connect users a list of features. And according to this information, websites can identify unique users and track these users' online behavior. When users visit a website, for example, cars.com, and this has a third-party advertisement. When the user search information on this website, the third-party advertisement also connects data from the users, for example, the time zone, user agent, content language, list of plugins, WebGL render. And according to this information, the third-party advertisement will create the user's browser fingerprint and send the both browser fingerprint and this user's search history to the advertisement provider. Next time, when this user visits another website, maybe a travel website, and this website also creates the browser fingerprint of these users and search on the advertisement provider database. If the fingerprint can match, this website will know the user's search history, and even this user visit a travel website, the third-party advertisement will also give this users the car's advertisement. About the previous work, our lab published a paper on the NDSS 2017. We create a website named Unique Machine, and we connect and analyze users' browser fingerprint on this website. And according to our approach, our fingerprint accuracy is very high. We already know that browser fingerprinting is a serious privacy problem that a lot of people try to fix them. For now, they have two existing anti-fingerprinting approach types. The first type is the randomization approach. A paper published on the 3W 2050 provides a system named ProVector. The limitation of this approach is if an attacker connects more data, it will fix the randomization part and get the real data. And the second way is the uniformity approach. Tor Browser try to use this way to fix the vectors, such as the user agent, get a unique result. However, for the WebGL part, Tor Browser disabled WebGL. This is sacrifice functionality over privacy. That's our purpose is we enable the WebGL and create the unique WebGL result. Let's talk about the rendering of WebGL task first. For example, if we have a WebGL project and the computer A rendering this WebGL project and create an image, also computer B also run the same project and create another image. Manually, we cannot see any difference between this image. But if we use the image A minus image B, we will find this difference. And the attacker can, according to this difference, to create the browser fingerprint. So let's talk about overview and the system design. To understand the difference of the WebGL project, we talk the graphics pipeline first. First step is the vertices. It's just the point information. When vertices transfer to the vertex shader, maybe can have some options, for example, the enlarge options, rotation options, and create the transformed vertices. Next, this point on the shape assembly, this point will create a triangle, and on the rasterization part, the shader will decide which pixel is in this triangle. On the fragment shader part, the shader will decide will draw every pixel, will give every pixel a certain color. And according to our research, we found that it's the floating point operations cause the difference. And all graphics pipeline step has this problem. And thus, we create a system named UniGL to make the floating point operations uniform. We will talk one by one. First is the vertices, just the point information. In the WebGL part, is the floating point coordinate system is from the -1 to 1. And we try to draw 3 points, V1, V2, and V3. V1 is 0.0, 0.0. And when we try to map this floating operation coordinate system to the canvas, for example, just 8 times 8 canvas, it is an integer coordinate system. It's from the 0 to 7. The computer A will draw the V1, 4, 4, V2, 2, 5, V3, 2, 2. However, the computer B maybe draw the V1, 3, 3, V2, and V3 is same. The reason of that because when they try to map from the floating point floating coordinate system to the integer coordinate system, they use the floating point operations. We know that in the floating point coordinate system, V1 equal to the 0.0, 0.0. And because the integer coordinate system is from the 0 to 7, V1 will become to the 3.5, 3.5. However, some computer will use the float option, and the other computer will use the round option. So they will get the different point. Next, we will talk the transformed vertices. It's just in the vertex shader points will have the maybe enlarge or rotation options and create the transformed vertices. And we know that the transformed vertices equal to the vertices times the matrix. For example, the world matrix, wheel matrix, project matrix. And we try to just make these vertices has a rotation option, and it just directly map a rotation matrix. However, we know that when they time a matrix, they also has the floating point operations, so it will cause the difference. And when we try to analyze the vertex shader, the problem we are found. When the JavaScript transfer the vertices to the vertex shader will have the floating point operations, and this part causes the difference. Thus, we transfer this part to the JavaScript. We use the JavaScript to create the floating point operations to create the transformed vertices. Also, according to the IEEE standard for floating point arithmetic, or that's the IEEE 754, we know that JavaScript will create the same result. Next step is the shape assembly and the rationalization. The shape assembly is just the points will create a triangle, and the rationalization is just the shader decided which pixel is in this triangle. For example, when we try to draw a triangle, in the WebGL part, it's a floating point coordinate system. And on the shape assembly, it will create a triangle, and then it's the rationalization part. Even we can make sure, okay, this 3 point, this location is totally same. The gray pixel is from the computer A, and the yellow pixel is from the computer B. We still found, okay, there are some pixels that belong to the computer B, but not belong to the computer A. Because in this part, where shader will use the floating point operations to decide which pixel is belong to this triangle. Even we can make sure the input of the shader is totally same, but the output of the vertex shader is not same. And when we try to analyze, this problem in the rationalization part, we have found, okay, it's the shader, it's the system floating point operations will cause the difference. Thus, we try to move this work on to the fragment shader. In the fragment shader, we try to use the GLSL integer operation to finish this part of work. First, on the vertex shader, we will draw 2 triangles to cover the whole canvas to make sure on the fragment shader part, we can give every pixel their colors. And then because in the JavaScript part, we already has the transform the vertex value in the JavaScript. and we can directly transfer this point location to the fragment shader point. It's just fragment shader. Also, on the fragment shader, we can use the GLSL integer operation to judge which point is in this triangle. If this point is in this triangle, we will give this point the triangle color. Otherwise, we will give this triangle the background color. The next step is the fragment shader. Fragment shader is just to give the pixel their color. And they have the 4 example functionality. The first is the single color. Single color will meet the same problem. For example, if we try to give a pixel, the color is 0.5, 0.0, 0.0, this is a RGB color. And then the computer A maybe will show the 127.00, and the computer B will show the color maybe 128.00. It made the same problem just like the vertices. Is when the shader try to transfer float range color to the integer range color, some computer will use the float option, and the other computer will use the round option. So the computer will show the different color. And we use the JavaScript to transfer the, in UniGL, we use the JavaScript transfer float value to the integer value. And we directly transfer the integer value to the fragment shader. On the fragment shader, we transfer integer value back to the float value. Also, we add a very small value to prevent the precision loss, because the different computer maybe have the different precisions. On the light part, the new color equal to the color times the light matrix. The relationship between the light and the single color is kind of like the transform the vertices with the vertices. Still, they have made the same problem. Is when they try to multiply the matrix, they use the floating point operations. And our solution is in the fragment shader part. We transfer the fragment shader floating point operations to the fragment shader integer operations. And the on the varying color part, if we try to draw a varying triangle, we give this 3 points their color. And the system will, according to the target point, the distance with these 3 points, to automatically create this pixel's color. And also, this is also on the shape assembly part, this is a triangle, and on the final part, there is the whole varying triangle. Also, the problem is still, even we can make sure this is 3 points, they have the same location and the same color, because the other pixels in this triangle use the shader floating point operations, so the result is still different. The same thing is still in the texture. In texture, we have the V1, V2, and V3. And in the texture, we also map V1, V2, and V3. We try to map the texture triangle to the canvas triangle. And also, they according to the target, to the distance with the V1, V2, and V3 to find the target in the texture. Also, because they have the floating point operation in the shader, the computer A and the computer B may be found the different pixel on the canvas, on the texture. So we try to fix this is in the fragment shader, we already use GLSL integer operation to judge which point is in this triangle. Also, after that, we also use the GLSL integer operation to calculate the varying color or the texture value. And in our implementation part, we implement our UniGL as a prototype. On the first part, vertices shader float, when we transfer vertex shader float operation to the JavaScript float operations, we spend 8,500 lines of JavaScript code. The second part, when we transfer the fragment shader float operations to the fragment shader integer operations, we spend 650 lines of GLSL code. On the other part, just the web assembly and the add-on part, we use the 3,000 lines of other code. Next, we will talk the evaluation part. In the test, we used 17 different rendering tests according to the DSS paper. First, we will run the 60 original text, and then we will run the 60 tests with the UniGL for the average computer. We will connect data from the Amazon and Mechanical Turks, and we already connect the 656 fingerprint result. According to the graph, we can see the Chrome, Firefox, and Safari will have a lot of unique fingerprint, and it will help to find the unique users. But our result just one. We just create one unique result. This is the detail of the whole 17 tests. The left is the original one. The right is the UniGL one. And according to the frame per seconds, we can see both the original one and our one is around 60 FPS. It's just match the screen refresh rate. The final is our conclusion. First, we analyze the reason of the render difference. Also, we propose UniGL to prevent WebGL-based browser fingerprinting. Finally, we implement an open source prototype of UniGL as a browser add-on. And this is our demo website. Thank you.
Thank you. We have some time for questions. Please queue up in front of the mics.
Hey, I like this work. I have one quick question. You are still running adversarially supplied GLSL fragment shaders on the GPU, right?
Yes.
What confidence do you have that there are no differences in the behavior of such programs besides the ones that arise from floating point?
It's just in our we connect data, and from the data we can make sure, okay, we create the same result. And also because we also consider, because this is the integer operation, and the integer operation is make sure, okay, the result is totally same.
But programming models involve more than just arithmetic operations on the numeric values, right? So there could be differences in cache behavior or other kinds of platform features.
Yes, I know that. I think this is a lot of detail I cannot say right now. Maybe we can talk later. Yeah, thank you.
Zephyr, you're from UCLA. Thanks for the talk. So I'm wondering if you look at the difference caused by different GPU hardware. So I think this difference is as a result of browser and WebGL, OpenGL libraries.
Actually, the difference is not only come from the GPU, it also comes from the browser, even the browser version, also the operating system and the driver version. So we try to analyze the every level one by one, but we found, okay, every level will cause a difference. So we just try to use we just try to find a unique operation to just transfer all operation to these unique operations.
Okay. Another quick question. Do you think just disable the read pixels will solve the problem?
Actually, they have, for example, if you disable the read pixel, it's just sacrifice the functionality. Yeah, I think maybe, yes, if you disable the read pixel, yeah, we can save the problem.
Yes, I don't think the API is well used. Right.
Yes,
yeah,
yeah.
Thanks.
Thank you.
Hey, Michael, UC Berkeley. So in your table of sort of performance impact, you mostly had relatively small scenes that were capped at 60 FPS anyway.
Yeah.
I mean, you're doing things like rasterizing in the fragment shader. Surely the performance impact with more complex scenes might only show when you start to do sort of complex things.
Yes, there are two reasons. First is our test environment. This screen is the 60 FPS, and we used a lot of way to improve improve our performance, we just use the web assembly. Actually, in the vertex shader part, if you see the detail on the paper, we compared every micro benchmark. Some part, even our system is quickly than the unique on the original one. So so using the fragment shader, we will waste some time, but in the vertex shader, actually we make it a little faster.
Okay, all right, thank you.
Thank you.
All right, let's thank the speaker again.
Thank you.